So now finally the last topic that we're going to cover is bit manipulation, and the reason that we're covering it last is because I think it's not really a super important topic, especially for coding interviews, but it's definitely something that comes up. So I think it's very important to at the very least understand some of the basic things that you can do with bit manipulation. And even beyond coding interviews, I think it's good to have a fundamental understanding of the basics. So there's a few logical operations that you can do with bits. Now, first of all, what is a bit? Well, we talked about it close to the beginning of the course. Bits are just zeros and ones. Computers basically use zeros and ones exclusively under the hood, but most of that ends up being abstracted for us. But let's start with a few fundamental operations. One is the AND operation. So with zeros and ones, we can do a logic AND, aka a bitwise AND. So for two given bits, suppose 0 and 0. Now we usually use this character, the ampersand character, to indicate a bitwise AND, and that's actually the case for most languages. So I'll summarize the main operations in terms of code. Now this is Python, but actually these operations are pretty much the exact same in most languages. So the logic AND operator is going to use this character. So 0 ANDed with 0 is the value 0. So basically what the logic AND means is that both bits have to be 1 for the result to be 1. But if that's not the case, the result is going to be 0 regardless. So if the first bit is 0 and the second bit is 1, then the result is still going to be 0. If the first bit is 1 and the second bit is 0, again, the result is going to be 0. But only in the last case where both bits are 1 is the result going to be 1. So that's where the name comes from, and both have to be 1, and then the result will be 1. OR is sort of the opposite. Only a single one has to be 1, and then the result will be 1. But if neither are 1, then the result will be 0. So this is the character for logic OR. And so continuing, 0 or 1 will be 1, because only one of these has to be 1. And then if the first one is 1 and the second one is 0, the result will again be 1, because only one needs to be 1. And if both of them are 1, the result will be 1. The third case is called exclusive OR, and this actually does come up occasionally in coding interviews. It's basically the result will be 1 only if one of the bits is 1, not if both of them are. So it's similar to OR, except it's exclusive OR. Only exclusively one of these can be 1, and then the result will be 1, not if both of them are 1. So the character for that is the up caret, kind of. So 0 exclusive OR with 0 is going to be 0. Exactly one of these should be 1 for the result to be 1. It's not, so we don't get a 1. But if we have the second one is 1, then we get 1 in the result. If the first one is 1, then we also get a 1 in the result. But if both of them are 1, we get a 0 in the result. So you can kind of take a look at these three and compare them. They're mostly straightforward, but if you haven't seen this before, if you've never seen these are called truth tables. Basically, these are some logical operations that we could do. This is not something you'll necessarily have to draw out in like a coding interview, but it's good to kind of understand the logical basics of what's going on here. Now, of course, there's the negation operator, which is the tilde in most languages. It'll just take any bit and take the negation of it. So, if we take the negation of 1, it's going to be 0. If we take the negation of 0, it's going to be 1. It's pretty straightforward. These are really the only two cases. The last thing is bit shifting. So if we have some binary integer, usually in programming languages, we're talking about 32-bit integers, but I'm not going to draw all that out because, it would take up a bunch of space and it's not super important to get the idea across. Let's say we had an integer that, was 001. So basically, this is the integer 1 in binary representation. Of course, we could draw out all 32 digits, but we're not gonna in this case. Now, if we take this and bit shift it to the left by 1, that's what we're doing down here. We're taking n, which is 1, and shifting it to the left by 1, and then assigning that to n. So what this would do is it would just take all these bits and then shift them to the left by 1. So by doing this operation, we would get a result of this. What if we did this operation again on this integer now? Well, then we would get a result like this. What if we did it one more time now? Well, assuming in this case we just have an integer with 3 bits and we have no bits to the left of it. Well, if we bit shift this one more time to the left, where does the 1 go? Because previously we were saying every bit was shifted to the left. Well, in this case, we have a 1 here. It's going to get shifted to the left, and then it's essentially going to be dropped off. It's going to be deleted. It's going to be replaced with a 0. It's not going to circle back here. It's just going to completely be deleted, and then we would have this as the result. This 0 would be moved to the left, and when this 0 is moved to the left, it's going to be always replaced with a 0. That's what we kind of saw throughout this example. When we shifted this by 1, it was replaced with a 0. When we shifted this, again, replaced with a 0. Now, one thing that's very important when we have a binary value, let's suppose we have 1, 0, 1, 1, this is the ones place, right? This tells us how many ones we have. That's how numbers are represented in binary. The next digit is going to tell us how many twos we have. So this is the twos place, and then the next digit is going to be the fours place, and the next digit is going to be the eights place, and it's going to keep going like that. Now this is somewhat comparable to if we were, suppose had base 10, if we were thinking about integers in terms of base 10, which is what we do most of the time. We're all used to thinking of numbers where the max value a digit can be is 9, and then if we get the value 10, we of course add a new digit for that, right? We count 1, 2, 3, we go all the way up to 9, and then when we get to 10, we add a new digit for that. That's called base 10. This is called base 2 because by the time we start at 0, then we get 1. By the time we get to 2, we add another digit for that. So this in binary is not the number 10, this is the number 2. That's why this is the ones place, this is the twos place, this is the fours place, eights place, etc., right? Each time we move to the left, we're getting a new power of 2. So essentially, this is 2 to the power of 0, this is 2 to the power of 1, this is 2 to the power of 2, 2 to the power of 3, which is 8, and it keeps going like that. That's how binary numbers work. Whereas with base 10, you have a number like this. This is the ones place, aka 10 to the power of 0, that evaluates to be 1. This is the tens place, right? This is not 3. This tells us we have 30 because it goes in the next spot. So this is 30, right? We're pretty familiar with that. That's basic math, but we call this the tens place, aka 10 to the power of 1. This is the hundreds place. This isn't 4, this is 400, right? So this is 10 to the power of 2. 10 to the power of 2, by the way, is 100. So it keeps going like that. This is the thousands place, etc., etc. That's why we call this base 10. So I wanted to kind of review that with you in case you weren't already familiar. And by the way, what happens if we take this and shift it to the left by 1 and we got something like this? 5 times 5, 4, 3, 2, and then we add a 0 in this spot, similar to how we were doing it with binary. Well, shifting to the left and adding a 0 when it comes to base 10 is essentially taking this and multiplying it by 10. If you're familiar with math, multiplying by 10 essentially adds a 0. Well, in terms of binary, when we're shifting to the left by 1, we're actually multiplying by 2. That's very important. That's a pretty basic and important idea to remember. As you shift to the left, you're multiplying by 2. This in binary is the integer 1. This in binary is the integer 2 because we have, something in the twos place. This in binary is the integer 4, and it basically keeps going like that. So that's bit shifting to the left. We can also bit shift to the right. So suppose we had a value like this. By the way, this represents the value 4. In binary, suppose we shift to the right by 1, we would get something that looks like this. Suppose we shift to the right by 1 again, we would get something that looks like this. Notice how as we shift, we took this 1, moved it to the next position, and then we replaced what was on the left with a 0. That's similar to what we did when we were shifting to the right. So now we're going to shift to the right one more time. We're going to get basically 0. And similar to how when we shifted to the left by 1, we were multiplying by 2. When we shift to the right by 1, we're dividing by 2. This is 4, this is 2, this is 1, and this is 0. So we're dividing by 2 when we shift to the right, but if we have an odd number, we're going to round down. So with all that being said, let's jump into an example problem where we're given some integer and we have to count the number of bits. So suppose we were given an integer like 23, which by the way, in terms of binary would look something like this. In most languages, it would be represented with a 32-bit integer, so we would actually have 32 bits. You know, in this case, we would just have a bunch. So in this case, we have 5 bits, so we would have probably 27 zeros that come before it, which would make this a 32-bit integer. But let's just draw out the 5 bits for simplicity's sake. And suppose we want to, given this integer, count the number of bits. Now, n in this case is going to be 23 base 10, but we know under the hood that's represented by some binary value that will look like this. So we want to count the bits of its binary representation. How can we do that? Well, we're basically going to use the same ideas that we talked about over here. We're given that as a parameter, we're counting the number of bits. Initially, that's going to be 0, while n is greater than 0. So suppose we're given an integer like 23 and we want to count the number of 1 bits in its binary representation. Well, in terms of binary, it would look something like this: 1, 0, 1, 1, 1. Now, most of the time you'll be using a 32-bit integer to kind of store this. Python actually has unlimited bits for values, but let's suppose we had 32 bits. Basically, since this is 5 bits, we would have 27 more bits, which are all leading zeros. So I'm not going to draw all of those out. We're just going to focus on these. And we want to count the number of 1 bits in its binary representation. So n in this case is the parameter. It's going to be 23. But we know every base 10 integer has some binary representation. In this case, this is what it looks like. We want to count how many 1 bits it has. In this case, it has 4. But how can we count them algorithmically? Well, it's not too complicated. We just need some of these operations that we already talked about. So in our function, we're given the parameter. We're going to declare count, which is going to, be the count of 1 bits. We're going to count while our value n is greater than 0. We're assuming we don't have to worry about negative numbers in this case. And we know that the value 0 itself, even in binary, will just be 32 zeros. So there's not going to be any 1 bits for that anyway. So now we're basically going to count 1 by 1. We're going to check the ones place. Is there a 1 bit here or is it 0? How do we know? Well, we can use the logic AND operator, the bitwise AND. By taking n, which is right now 23, and bitwise ANDing it with 1, we're going to get an operation that looks something like this. This is what 1 looks like in binary. Of course, it would have a bunch of more zeros, but we don't care about those zeros. So when we bitwise ANDed single digits, we had this truth table over here, and this will help us out. When we bitwise AND multiple bits, it's basically taking each of these and taking the bitwise AND of them. So we know that for these two, it's going to be 1. And for this, it's going to be 0. For this, it's going to be 0. For this, it's also going to be 0. And for this, it's also going to be 0. Because both of the bits have to be 1 for us to get a 1 in the result. Now, let me tell you something. When we take any number and bitwise AND it with 1, the result that we get is always going to be either 0 or 1. The reason is because this is 1 in binary. It has only zeros here. So we know everything in the result is going to be 0, except possibly this digit. And it's all going to depend on what this digit happens to be. If this digit is a 1, we're going to get a 1 in the output. If this digit is a 0, we're going to get a 0 in the output. We're using the value 1 because it's special. It has all zeros except for this bit. So this will tell us if we have a 1 in the ones place or not. So in this case, we are going to get a 1. So this is going to evaluate to true. So then we're going to increment our count by 2. And then what we're going to do is take our n and shift it to the right, which we know is the same as dividing by 2. So when we take this and shift it to the right, we get something that looks like this. Right, we're basically chopping off this bit. We don't care about it anymore. Then we're taking the rest of these, shifting it by 1, and then we're replacing the leftmost digit with a 0. Now we're just going to repeat the same thing until this value becomes 0. So we're going to take the digit 1, the value 1, bitwise and these together. In this case, we're going to get a 1 in the output because this is a 1. And then we're going to increment our count by 1 again. So far our count is 2. We've counted 2 1 bits. And we're going to basically do the same thing. So now this is going to be shifted to the right by 1. We're going to get something like this as the value. We're going to check is this a 1 or not by taking the bitwise and. It is a 1. So now our count is going to be 3. And then we're going to shift this to the right by 1. We're going to get something that looks like this. Now we're going to bitwise and this. So we're going to check, is this a 1 or not? We're going to get a 0. So this is not going to evaluate to true. So we're not going to increment the count by 1. Our count is still 3. And then, of course, lastly, we're going to take this, shift it to the right by 1. We're going to finally get this. We're going to check, is this a 1 bit or not? It is. So we're going to increment our count. Our count is now going to be 4. And then we're going to shift this to the right by 1 again. And at this point, it's going to be 5 zeros. So our conditional is not going to execute anymore. So our loop is going to stop and we're going to return the count that we calculated, which is 4. So we had 4 1 bits in this particular integer, which is 23. So 23 has 4 1 bits. So we didn't go super in depth in this because I don't think it's super worth going into. I think understanding the basics is probably enough. And there are some practice problems in the practice section if you want to practice more bit manipulation type problems. Usually they just require a bunch of tricks, which is why I think they don't really come up super often in coding interviews because they don't really make for good coding interview questions. Either you know the trick or you don't. So they're not the best coding interview questions in my opinion. But these basics that we talked about definitely can come up even outside of coding interviews. So it's good that you have now learned them.